important impression.
Yeah.
Okay.
All right. Thank you, Omar. Okay. Okay. Good luck. All right. Next. Okay. So the next presenter will be Sarah.
Yeah.
Sarah Al-Tariq.
Yes. Hello, doctor. How are
Al-Tariq.
you? Okay.
Alhamdulillah. How are you?
I'm all good. Okay.
All right.
I am presenting my screen now. Can you see
So
it?
you are in Malaysia or
Yeah, I
where?
am in Malaysia.
Yeah. Yeah.
Yes. Are you see? Can you see my
Okay.
screen? Can you see?
All right.
Yes.
Okay. Can I
All right.
switch
Yeah.
off the
Yeah.
video to reduce the traffic for the internet?
Okay. Later during the Q&A, you can.
Yeah. Okay. Sure. So, Assalamu alaikum and good afternoon, Dr. Norsham and Dr. Norizam. It's really great to have you as my evaluators today. So, my name is Sarah Tare and the research paper is titled Investigation on Java Mutation Testing Tool, and my supervisor for this work is Dr. Ruhayan Hassan. So, in this presentation, I will walk you through the introduction, literature review, methodology framework, experimental setup, my plan for FYP2, and the conclusion. So, without further ado, let's begin. So, as you know, software testing counts as one of the most significant phases within the software development lifecycle, since software bugs can be costly and traumatic. And to perform the typical software process, specifically speaking here, white box testing, we create test cases to exercise the inner workings of the software under test, where we compare the expected results with the actual outputs. However, this is not enough on its own, where some undiscovered faults might still exist due to the test case's inability to detect underlying faults. And that is why many techniques have been developed by researchers to solve this issue. And among the variously proposed techniques comes mutation testing. So mutation testing is a fault injection technique where we intentionally introduce errors into the application being tested to assess the quality of the test suite. The technique is claimed to be one of the most adequate approaches for assessing the quality of a test suite by Aman and Uhud, and is also deemed to be effective to the point of subsuming almost all other techniques. However, despite its effectiveness, some problems still lay within the technique that shall be addressed. The first problem is the dismissal of the mutation testing technique by many practitioners despite its effectiveness, and that is because the technique is very time consuming and there are some hefty expenses associated with the procedure. Not only that, but the technique also requires substantial computational resources that call for large storage space, and that is why, to save time and effort and resources, we should use an automated mutation testing tool that is fast and reliable. The second problem is that different results could be obtained for the same test suites, and that is because the strength of mutation testing highly depends on the set of used mutants in the mutation process. Thus, to prevent the occurrence of this issue, it is important to identify the most optimized set of mutation operators to generate mutants which effectively assess the adequacy of the test suites. And the third problem is that there is a diversity of mutation tools for mutation testing, where each tool has its different applications, restrictions, and set of used mutants. And the different implementations and limitations of the tools can lead to different results in terms of the effectiveness of test suites. Thus, to prevent this issue, we shall choose from the various tools out there a reliable tool in terms of performance and capability of generating mutants. So the main objectives of the study, which are determined based on the listed problems stated earlier, are as follows. The first is to conduct a systematic attempt to evaluate the different mutation testing tools for Java, where the efficiency of the mutation operators for each tool in the study will be identified, examined, and compared using two open source Java applications, which we will discuss later in the presentation. For the second objective is to determine how well these tools are performing, and this will occur through running these tools against the Java applications chosen to generate mutants via the mutation operators for each tool. And then accordingly run these mutants against the test cases accordingly and compare their behavior with the behavior of the original program. And lastly is to evaluate the effectiveness of the mutation operators via mutation score. So the research aim of this project is to inform the practitioners about the efficiency and inadequacies of the two selected Java mutation testing tools, along with their affiliated set of mutation operators. So the scope of the project, this research presents an investigative study of two distinctive Java mutation testing tools, PIT-tool and MuJava. The study aims to pinpoint the weaknesses and strengths of each tool involved through performing mutation testing on two open source Java applications, quadratic.java and tritip.java, to identify the best mutation tool among them in terms of efficiency and effectiveness. The study aims to further identify and compare the mutation operators for each tool in terms of quality, effectiveness, and fault detection rate through calculating the mutation score. Okay, that is all for the introduction. Now moving on to the literature review. So as we have just discussed, mutation testing is a fault injection technique where faults are introduced into the code via mutation operators to produce faulty version of the programs known as mutants, and that to test the error handling of the system. So what is a mutation operator and what are mutants? First, mutation operators are actually a well-defined rule introduced into the original program to either replace, delete, or insert a syntactic program modification into the source code. And the aim is to imitate the common mistakes that the developers make. So here, this is an example of the mutation operators. Here we have the original program, and then here we have an OR operator. So via introducing a mutation operator, we change the OR operator, which becomes an AND operator, and that faulty version of the program is known as mutant. So the process of mutants generation could be illustrated as follows. We have the original program, and here in the original program, as you can see, we have the addition sign. So we generate now mutants via the mutation operators, as we have just explained. And here we change it. Here it becomes a subtraction, multiplication, and so on. And these are called mutants, which are the faulty versions of the program. So here, to illustrate the whole process of mutation testing in the software testing process, the normal testing process, we have the original program where we create test cases for. So what we do is that we run these test cases against the original program, and then we check, is the program correct? No. If the program is not correct, we fix the program, and then we run it again. We run the test cases again over the program. We keep on repeating all of that until the program is free of errors. Okay, that is for the traditional software testing process. So here, to further ensure that the correctness of the program, we perform mutation testing, where here we're gonna via the help of mutation operators, we're gonna introduce the mutation operators on the program and accordingly generate mutants, where we have the mutated program now. So what we're gonna do is we're gonna do the same thing exactly, but however this time it's gonna be on the mutated program. So we are gonna run these test cases against the mutated program, and then we're gonna see, is there an error detected? If there is no error detected, that means that the mutant is alive and that the test cases were not able to detect the mutant introduced. So that drops us to the conclusion that the test cases are inadequate. However, if the error is detected, that means that the mutant is killed and that the test cases we have are adequate. So as we have explained in the problem background, mutation testing is usually rejected by the software testers due to the costs affiliated with the strategy. So there are some strategies introduced to reduce the cost. The first strategy is to reduce the execution cost, and the second strategy we're gonna talk about is to reduce the runtime costs. So for the execution costs, we have something called strong mutation testing and weak mutation testing. The strong mutation testing is known to be, it's also called traditional mutation testing. And here, the state of the program is compared after the execution of the entire module. However, for the weak mutation testing, which is known as Do Smarter, and it's proposed by Howden, the state of the program is compared after every execution of the component. So what is the difference here between these strategies? The cost of weak mutation testing here is less than that of strong mutation testing, where it's less computationally expensive and it also reduces the test effort. Now for the runtime optimization technique, traditionally in the traditional mutation testing process, the mutation is inserted into the source code and then it gets compiled, and that is known to be costly. So we have something called bytecode translation. In the bytecode translation, it manipulates the Java bytecode directly using bytecode manipulation and analysis frameworks provided by the Java platform. It is performed on demand during the runtime, since we optimize during runtime. It is easy to use and it reduces costs. And here for the cost reduction, there's an experiment that's done by MA and Ufut. So here they have classes of the program, and then they have generated mutants for these classes. And they have compared bytecode via source code. So as you can see, this is the time needed to execute bytecode. The process required 33,000 milliseconds. However, for the source code, for the same classes and the same mutants, it took 183,000, which drops us to the conclusion that the bytecode is more efficient. So for the selection of the tools, now we have 5 tools for Java mutation testing, and I have compared the Java these different tools according to the characteristics. So some of these tools support object-oriented operators and some others don't. So for Pit and Mujava they support, however for Jester and Jumble they don't. For the mutation generation level, Pit and Mujava support bytecode. However, Jester, Judy, and Jumble they support source code. The type of mutation testing for Pit and Mujava, they use weak mutation testing, which also we explained earlier. They are more efficient. And for Jester, Judy, they use strong. And the 5 mutation testing tools they support JUnit automation testing framework. So that is for the comparison between the available mutation testing tools for Java. Now moving on to the methodology framework. So the methodology of this research is going to be carried out. It was carried on 4 different phases, where the first phase is the literature review. So first we have reviewed recent studies on mutation testing. Then we have reviewed the mutation testing tools for Java. And the selected tools are Mujava and PitTest. And accordingly, we have reviewed the mutation testing operators for these tools, Mujava and PitTest. Moving on, we have identified the problems, where we identified the limitations and gaps from the systematic literature review. And we also defined the research scope and objective. And from that, we move on to the experimentation and evaluation, where the experiment setup is done, then the experiment is operated, and then the result is evaluated. And then moving on to the 4th phase, which is result dissemination, achievements, contributions, and future work is done, report documentation, and thesis completion. So for the evaluation metric, we're gonna use mutation score here. And what is mutation score? It is a fault-based technique to measure the effectiveness of a test suite in terms of fault detection rate. So here we detect the total number of killed mutants over the total number of generated mutants, and we multiply it by 100 to get the percentage. Okay, so why Mujava and PitTest? Justification to the tool selection. So again, both of them are open source tools which we can easily get. They both use weak mutation, which is deemed more better than the strong mutation. They both use bytecode translation, which is also, as we have explained, they are better than the source code translation. They both support object-oriented features of Java. They both have support for JUnit, and for Mujava, it provides a documentation of the results. And for PitTest, it also provides an HTML report. The hardware and software requirements for the projects are the hardware requirement. We require an Intel Core i5 with a 16 GB RAM and a Windows 64 bits operating system. And for the software requirements, a Windows 10 to support the installation of the mutation testing tools. Now moving on to the experimental setup. So for the experimental design, we first installed the tools. For Mujava, it's installed from the developer's website, and for Pit, it's installed using Maven plugin, and then the setup of the tools occurs, and then afterwards we install the programs that we're gonna use, the Java programs, which is the first one is quadratic.java and the second one is tritip.java, and then afterwards we here perform the mutation testing process, where we generate and execute mutants for program 1 using Mujava, then we do the same for program 2, and we also do the same with Pit. We execute the mutants and we generate and execute mutants for using Pit on quadratic.java and also tritip. And then after all of that, we calculate the mutation score. And the mutation score, we're now gonna use it to evaluate the performance of the mutation operators with respect to the mutation score. And this is the installation configuration process for the tools. Okay, the subject programs, quadratic.java and tritip.java. So quadratic performs, it calculates the roots of a quadratic, and for tritip, it's a program that calculates the type of triangle. And for the features of these two Java projects, they support object-oriented features, where they use classes and methods. And also for FYP1, I have introduced two subject programs. However, for FYP2, I might upgrade and use also test on more programs. So the plan for FYP2, I want to review the document I have proposed for final year project 1, the objective, scope, program background, literature review, methodology, and so on. And I'm gonna do mutation testing where I reconfigure the environment if needed, and then I'm gonna start to execute the mutation operators on the tools and perform the mutation testing as we have explained. And then we are gonna compare the tools and then make a statistical analysis report. And then so the conclusion of the project, we're gonna perform mutation testing on 2 Java applications as we have explained using PyTest and Mujava. We're going to reduce the cost of mutation testing via weak mutation and bytecode translation, as I have just explained also. And I will identify, evaluate, and compare the tools operators in terms of quality, effectiveness, and fault detection rate through calculating the mutation score. So that was all for my presentation.
Okay, thank you very much, Sarah. Okay, Norizam.
Okay, Assalamualaikum, Sarah.
Salam.
Okay. What is the expected finding or expected outcome from this research? Okay.
What do you mean? Like what I'm expecting to achieve from this research?
Yeah. Because from the aim, you said this, you will use this to inform the SE practitioner out there about blah 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 blah, right?
Yeah.
Okay.
Your hypothesis, maybe.
Yeah. So what I'm trying to do is that, as I told you, I have like first I got the tools, and then I selected the 2 tools as I showed you, PyTest and Mujava, according to the types, and then accordingly I want to know which tool is actually more effective, because when I detect which tool is effective, I'm gonna help the researchers know that which tool is most adequate. So I'm gonna do that by testing using the same tools on the same programs, and accordingly I'm gonna compare their results. And from these results, I'm gonna detect which tool is more effective in terms of the mutation operators and the tool overall, in terms of the performance of the tool.
Okay. How can you measure the effectiveness, the efficiency of that tool?
Via mutation score.
Yeah. Okay. What I understand about this mutation tool is, okay, mutation basically we have original problem. Okay, and we mutate it into version 1, version 2, version n of mutants.
Yes.
Okay, and the purpose of this mutation testing is to check the quality of our coding, right?
Yes.
Our original code.
Yes.
And as well test the quality of our test cases, test suites.
Yes.
Okay.
That is correct.
Tool is just a tool. So tool is just a tool to generate mutants based on standard mutation operators, right? So how you can measure the effectiveness of that tool?
Okay. So the tools don't just execute mutants. That's not what the tools do. The tools should execute mutants using the mutation operator, knowing that each tool has its different mutation operators. Okay, so PyTest, the operators for PyTest is different than the operators for Mujava. So I'm gonna use the tools to execute mutants against the original program, and from these programs I'm gonna compare I'm gonna test it using the test cases, and then I'm gonna can I show you from my report, my FYP report?
Yeah.
Okay. Okay, yeah. So here, so this is for Java. Yes. So
sorry. So from there, you want to measure the effectiveness by compare the score. How many mutants killed by the test case?
By the test cases,
by that, right? Okay. So you will use the same test cases for those 2 tools.
Same test cases and same test tools. I'm gonna use the same exact programs and same test cases. However, I'm gonna use it once via Pyt and once via Mujava, because the operator's effectiveness differs. So maybe PyTest have more effective operators than Mujava. So I'm gonna detect that. We're able to detect that through the mutation score. So I want to know which operators are actually more effective, those of Mujava or those of PyTest, because we have the same exact program.
In killing the mutants.
Huh?
How effective in killing the mutants?
Yes.
Yeah. Okay.
So that's gonna be concluded from the mutation score that's calculated later, after finishing the mutation testing process.
Is that, Sarah, is that the way how previous work, previous researcher do?
Yes, this
Did
is supposed to be the way.
Huh?
This is the traditional mutation testing process. This is how the mutation testing is performed.
Okay, Dr. Norizam, boleh saya nyambut?
Yes, please.
Okay. On the selection of the program, okay, that you provide the program, right? The quadratic, and another one is what is that?
Tritic.
Okay. So what are the criteria actually that of the program that you select?
Okay. So of course, so what I'm doing is that I'm testing on Java. So the first requirement is that I wanted the programs to be Java programs. The second thing, as I explained in the presentation, I wanted them to support classes and methods, because I want to test it on an object-oriented level, not just the structural level. So this is why also I chose like this. These were one of the reasons contributed to the selection of PIT and Mujava aside of the other test tools, because they support object-oriented features. So I want to test the object-oriented features of the tools. So I wanted the Java programs to contain classes and to contain methods. So accordingly, I can test the object-oriented operators of each of the tools.
Okay.
Okay. So how about other researchers? Did they use the similar test cases? The similar case study, the similar Java program?
For PIT and Mujava?
Yeah.
Yes, they're gonna use the same program, because I want to compare, like for the same program, how well is this one gonna perform and how well is this one gonna perform. So I have two programs. For the first program, how well PIT is performing, how well Mujava is performing, and also another program, how well PIT is performing, how well Mujava is performing. And accordingly, I'm gonna see which tool is actually better, PIT or Mujava.
Okay, and in that case, I think, what about the test cases? Test cases also play an important role, or you need to have a valid test cases. You can have a bad test cases, a good test cases, excellent test cases. So how do you, how can you say that or validate that this is the correct or the valid test cases to test?
Okay. So normally the test cases should all be passed, right? Because the programs I'm gonna test, the test cases should all pass. I want the test cases to be passed.
In normal program.
Yes. Because the mutation
program,
testing comes after the traditional mutation software testing process. So now, since all of the test cases passed, that's how we detect that they are correct, by them passing. So when I start the mutation testing process, all of the test cases actually should all pass, be 100% correct. And then after I execute the mutants and test on them, we should start detecting that some mutants are killed, some mutants are alive, and so on. So that now we start knowing, okay, this test case is incorrect, this test case is incorrect, according to the number of live mutants and also number of killed mutants. And also that's like the number of killed mutants and live mutants, that's the mutation testing score, which is the evaluation.
Yeah, but okay, sorry. So, for example, okay, test cases number 3 might kill mutant in Mojava, but it might pass, not kill the mutant in apa tadi? What's the program?
PIT.
PIT test.
Yes.
PIT test.
Okay.
Yeah.
So that means that in PIT the mutant is alive.
So your test cases need to be neutral.
Yes,
right?
it is the same
or
test cases. No, but actually the mutation testing process, the efficiency of the process depends on the operators. So what kind of operators of PIT and Mujava, this is how, like, this is why the tool selection is important, right? This is why I'm doing my study. I want to know which tool is actually more effective. Is it PIT or Mujava? Because the mutation operator of each tool differs, right? So maybe for PIT it has passed, and maybe for Mujava it didn't pass. So that means that Mujava is not effective. So that it's not about the test cases, it's more about the operators used in the process and also the results I achieve I can see from the experiment. Do you get my point? I hope I'm
Okay,
clear.
fair enough.
I hope
Fair
I'm
enough.
clear.
Yeah. But test cases also play important role because the use of this mutation test
Mm-hmm.
is to check how good the test cases
Yes.
are.
Mm-hmm.
Right?
Yes, yes.
Yeah. Okay.
So,
Okay.
That is correct.
Thank you.
Inspector Norizam, are you suggesting that the test cases also had to be some sort of verified
Yeah,
or
verified. Yeah. Because that's the bullet that you want to use
Mm-hmm.
to kill
Mm-hmm.
both mutants in both sides.
How to verify
So
that
you
the
need
test
to
cases are correct.
verify that test.
Yeah.
You are using the neutral bullet to verify that test
Yeah, I
cases.
get you. Actually,
Okay.
how you
Thank you.
identify, like without the mutation testing process, as I told you, how we know that these test cases are correct. Can I go back to the presentation? Is it okay
Yeah.
to show you from the slides? Okay. Uh, okay, so here if you can check, in the normal testing process, we want to make sure that the test cases are efficient, right? So we check after running the test cases on the program. Is the program correct? If it's not correct, we keep on fixing until see we have a loop to fix to keep on fixing. So after here it should be everything should be correct. The program should be correct and the test cases should pass. However, here in the mutation testing process, like normally in the normal mutation testing process, if you can check, if the test cases are inadequate, here there is a line that goes to the test cases to fix it. So here, when they are deemed inadequate or an error shows, that means that there's a problem with the test cases. So we fix it. This is the normal process.
Okay. Fair enough.
Okay, Sarah. So based on your objective, that is, so now you have already achieved which objective? One and two, is it?
The objectives, okay, so I have identified, can I go back to the objectives, please?
Never mind. I think you can just explain which
Yeah.
objective that you have achieved.
Okay,
Okay.
so actually what I have done is that I have evaluated different mutation testing tools for Java, as I told you, the 5 different tools, and I detected according from that Mujava and PitTest. I selected these because they are the best performing tools among the Java mutation testing tools. And then here I'm supposed in FYP2, when I do the mutation testing process, I will be able to determine how well they are performing, and I will also be able to do the evaluation. So for FYP1, I have achieved the first objective, which is to identify the tools. And then later on for FYP2, when I perform the mutation testing process, I will be able to achieve the other 2 objectives.
Okay. So in your conclusion, okay, please mention that, okay, mean that the achievement, okay, based on the objective. Okay, so we can see the relation between your what you have achieved, what you have
Yeah.
achieved with the this objective.
The conclusion
Okay.
was the conclusion of the presentation, not the project.
No, I mean in the report,
Okay.
Okay.
All right.
The report.
All right.
And also, you also mentioned, okay, in your framework, you conduct the SLR, systematic literature
Yes.
review, but that one only appear in the diagram, but not in the report. And
Yeah, for the report, actually,
what,
I have.
okay, what I understand is actually what you presented in the literature review is not actually SLR. Okay, SLR, it has its own. I mean, the approach is quite different. Okay, so I think that you can just remove the word SLR in your framework, in your diagram there.
Okay, so it's
Okay.
literature review, not systematic. I don't get it.
Yeah, it's literature review.
Oh,
Okay, not
okay.
SLR.
Okay.
Uh,
All right.
okay. Okay. So I think that's all from me.
Okay.
And please consistent. Okay. In your report. Okay. In some part. Okay. You write as mu, and and another part you write as the
It is
mu.
the same. When it's written, it's sometimes they use the symbol and sometimes they write it with an M. So it
But
can
the
be
name
used alternatively.
I think you must consistent.
Make
Okay,
it
because
uniform throughout the report. Okay.
all
All
right.
right. Okay.
Okay, so that's all for me. Dr.
Okay,
Norizam.
thank you. Thank you.
All right.
Okay.
Thank you so much.
Thank you, Sarah.
All right,
Okay.
thank you.
Thank you. Okay, the next presenter is